All right, so let's continue here with 3.1, and let's do a little bit of an algebra review here before we do some more derivative problems of relative extreme up. Now we have seen how to find the relative max and min of these polynomial functions and the examples that we did in the last videos, how to find their critical numbers, determine whether those critical numbers tell us where our function has a relative max or min. But again, the last three examples that we looked at were all polynomial functions. We haven't done any rational type of equations just yet. Because what we need to do here before we look at any examples involving rational functions is do some algebra review, specifically review how to find the asymptotes of a rational expression. Okay, so recall from algebra what a vertical asymptote is. A vertical asymptote occurs when a rational function, which I'll denote as f of x divided by g of x, a rational function of f of x divided by g of x has a vertical asymptote. Has a vertical asymptote, which I'll denote as VA from now on, has a vertical asymptote at x if for some x value, if we evaluate the denominator, the bottom function at that point for x, and if it gives us 0, but the numerator is not equal to 0. All right, in other words, recall, a vertical asymptote is a value of x that makes the denominator of a rational function 0. Okay. To define vertical asymptotes, we have to figure out what values of x can we plug into our function that will make the denominator 0. All right, so let's outline the steps here in order to on how to find these vertical asymptotes. All right, so in order to find vertical asymptotes, the first step is actually to simplify your rational expression. All right, don't just try to solve for the denominator just yet. Simplify it first. Simplify your rational function by factoring and canceling out any common factors between your numerator and denominator. And then after we simplify, then we set the denominator equal to 0 and solve for x. All right. And our vertical asymptotes will be the solutions that we obtain from that second step. And so the vertical asymptotes at x will be the solutions from step 2 here. Okay. So like say, for example, suppose we want to find the vertical asymptotes, which again, I'll denote as VA from now on. Let's find the vertical asymptotes here of the following function of x, which I'll denote as f of x equals, let's see, 3x plus 6 over x minus 2. All right, so 3x plus 6 over x minus 2. Now, the first thing we want to check here is we want to see if we can simplify the given rational any further. All right, so again, here we have f of x. Let's see, what can we do here? For this, let me write the equation, 3x plus 6 over x minus 2. So what can we factor out here from the numerator? Well, in the numerator, these two terms have a 3 in common. So we could write this as 3. So we can factor out 3, leaving us with the inside x plus 2 over x minus 2. Can we cancel these two out? No, right? Because we have a different sign in the middle. X plus 2 is not the same thing as x minus 2. So in this case, there is no common factor between the numerator and the denominator. In other words, since we're not able to cancel out anything from the top and the bottom, then this function has no hole in it. We come from chapter 2. Any common factors that we could cancel out in a rational expression represents a hole, a jump in that function. But in this case, since there's nothing in common, then we have no open circle, we have no hole here in this rational expression. In other words, this is already simplified. So now for the second step, take our function here and set the denominator equal to 0 and solve for x. All right, so now we're going to take our denominator here of x minus 2, set that equal to 0 to give us x equals 2. Meaning, if we plug in 2 into our original function here, if we plug in 2 into this function, the denominator will become 0, making this function undefined. All right, in other words, the vertical asymptote represents the points of x that makes your function undefined. So here, go to the third step now. So here we have found one vertical asymptote at x equals 2. All right, and when you're specifying the values of vertical asymptote, you don't just say 2, you have to say x equals 2. So be careful on the homework and the format they want you to answer these type of problems in. Okay, for asymptote, we usually denote as x equals whatever your solution was. Okay, let's do a second example here. Let's do another example, and let's find the vertical asymptotes of the following function here. All right, so let me kind of section this off. All right, so f of x equals, let's see. Let's do a quadratic over another quadratic. So x squared plus x minus 6 divided by x squared plus 4x plus 3. Okay. So again, the first step we want to try to do here is, can we simplify this given function? All right, so let me write our equation. So here we have x squared plus x minus 6 over x squared plus 4x plus 3. And let's factor out this quadratic on top and the bottom. So the top, x squared plus x minus 6, that factors that into x. What would that be? Negative 6, x plus 3 times x minus, 2. And at the bottom, this is going to factor out into, 4 in the middle, 3 third term, x plus 3 times x plus 1. Okay, well, what do we notice here? We notice that we have a common factor between our denominator numerator here of x plus 3. So x plus 3 gets canceled out. Meaning at x plus 3 here, if we set this equal to 0 and solve for x, that means then at x equals negative 3, we have a hole in this rational function. All right, so therefore, we have a hole at x equals negative 3. All right, so not a vertical asymptote here. Instead, we have a hole at x equals negative 3. Okay, and now for a simplified function, we're left with f of x equals x minus 2 over x plus 1. And now that we have simplified this rational, then we set the denominator equal to 0. So x plus 1 equal to 0. Solve for x gives x equals negative 1. Meaning that what we have left over here, since negative 1 can still make the denominator 0 even after simplifying, the negative 1 here is representing a vertical asymptote. So we have a vertical asymptote at x equals negative 1. Okay, so for this function, we have a hole at x equals negative 3 in a vertical asymptote at x equals -1. All right. So again, a vertical asymptote represents the values of x that will make your rational expression undefined after simplifying. In other words, it's the values of x that makes your denominator 0 after simplifying your rational expression. Okay. Now, so the vertical asymptotes deals with the x-axis. Okay, and we'll graph this in just a little bit. Horizontal asymptotes, on the other hand, recall deals with the y-axis. Which is known as HA. Okay. And horizontal asymptotes deals with the limits of a function. Okay. A function has a horizontal asymptote. At y, oops, I can spell that, asymptotes. At y equals L if the following is true. Okay. So function has a horizontal asymptote at y equals L if the limit as x goes to infinity of our function equals that value of L, or the limit as x goes to negative infinity of our function equals L. In other words, if we're going from left to right along a function and it reaches its limit at L, then that L is representing a horizontal asymptote. Or if we're heading towards negative infinity and we reach the same value of L, and that value is our horizontal asymptote or break along the y-axis. Okay, the vertical asymptote is a break along the x-axis. The horizontal asymptote, asymptote, let's spell that here. The horizontal asymptote is a break along the y-axis. Now, to find our horizontal asymptote, and again, what we have to do is find the limit of our function as x approaches infinity, or has to approach infinity. And what we're to go about this is use the methods that we saw in chapter 2, set up a table, see what the values of a function is approaching as x is getting larger and larger and larger. Or another option that we have here is to find this limit by dividing each term in the numerator and denominator, so each term in our function, by the highest power of x in the denominator. Okay, so we could either use a table method like we did in chapter 2, or use this other method that we have by dividing each term by the highest power of x in the denominator, and then find the limit of what's left over. Okay, so let me set up an example here. Let's find the horizontal asymptote of a function that we worked at earlier. All right, so recall earlier in this video, we found the vertical asymptote of this rational. Now let's find its horizontal asymptote. Let's check it. Everything's good. Still looking good. All right, so let's find the horizontal asymptote of f of x equals 3x plus 6 over x minus 2. All right, so again, to find the horizontal asymptote, it will be equivalent to taking the limit as x goes to infinity for this function of 3x plus 6 over x minus 2. Again, one option that we had to find this limit is to set up this equation and set up a table and plug in increasing powers of 10 into this function to see if there's a value that this function seems to be approaching. All right, the tables, the methods that we saw in chapter 2, when it came to limits, going to infinity. But the other option that we have is to divide each term on top and divide each term at the bottom by the highest degree power of the highest degree term of x and the denominator. Okay, and what's our highest degree here? Just x to the first. So we divide each term by just x. All right, so here we take the limit as x goes to infinity of 3x over x plus 6 over x over x minus 2 over x. So dividing each term by the highest power of x here. And then simplify where we can. Okay, so in this case, in this first term, since we have x and x on top and the bottom, these two will cancel out. 6 over x, can't do anything else with that, so that remains the same. But in the bottom, we also have x over x, so this also cancels out. And then negative 2x, nothing we can do further here, so that remains negative 2x. So now, we want to find the limit as x goes to infinity of what we have left over, which is 3 plus 6 over x over 1 minus 2 over x. Again, be careful. X over x, x divided by x is 1. Okay. So now, using the rules from what we saw in chapter 2, find the limit of each individual term here as x goes to infinity. Okay. So the limit of, so here we're going to pretty much take the limit of each individual term. What is the limit of 3 as x goes to infinity? Call chapter 2. What's the limit of a constant as x approaches some number? What is the limit of a constant? Okay, what do we call? From chapter 2 here. The limit as x approaches some number c of k, where k is a constant, is just equal to that constant. Okay. So in this case, the limit of 3 as it goes to infinity is just 3, which also means the limit of 1 as x goes to infinity is also just 1. But what about these next two terms? Okay. But let's see here. Here we're trying to find the limit as x goes to infinity of 6 over x of a constant over a changing variable. The tops can remain the same no matter what x is, but the denominator, as x goes to infinity, the denominator is just going to get bigger, bigger, and bigger. What happens to a fraction if the top stays the same, but the bottom gets bigger and bigger and bigger? Okay, well, as x gets bigger, bigger, bigger in the denominator, 6 divided by x will get closer and closer to 0. Okay, so the limit of 6 over x goes to infinity, is going to become 0. Let me make this note here somewhere. I'll put it on the side here, just so we can fit it here. That's a note. The limit, I believe I mentioned this in the chapter 2 videos as well. We call it the limit of x goes to infinity of a over x to the n, where a is a constant, is equal to 0. All right, for any constant a and positive integer n. And for any constant a and positive integer n. Okay. If the top remains the same, doesn't change, but the bottom keeps getting bigger, 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 then this calculation gets closer and closer to 0. So the limit of 6 over x as x goes to infinity is 0, And the limit of 2 over x, x goes to infinity, also is 0, leaving us with 3 over 1, or in other words, the limit of this function is going to be 3. The limit of this function, x goes to infinity, is going to be 3, indicating that we have a horizontal asymptote at y equals 3. Okay, so for this function of 3x plus 6 over x minus 2, we found a vertical asymptote at x equals -1. And now we, not x equals -1, we found a vertical asymptote at x equals 2 for that function of 3x plus 6 over x minus 2. And now we have found a horizontal asymptote at y equals 3. Let's visualize this. Let's look at our calculators. Let's draw this function here. Okay. So let's see. So we had parentheses 3x plus 6, parentheses divided by x minus 2. All right, let me set the window here. I'll do default 1010s. That should be good. What in the graph? Let's see. The function was 3, 6. Oops. Oh, that's why. Parentheses error. That should be x minus 2. You gotta be careful with those parentheses. We're entering those functions in your calculator. And there we go. Let's see if I can zoom out a bit more. It's much easier to draw this on the physical calculator than this app. So here we go. All right, so notice here, this blue line in the middle, that's representing that jump along the x-axis. In other words, that blue line that we have in the middle here, that is our vertical asymptote at x equal 2. Let's see if we can get the units a bit more. Oops. All right, just trying to see if I can get those values now. It's a bit annoying. There we go. So much work to do this. Okay. So x equals 2. That's where we have that break along the x-axis, that vertical asymptote. But now notice here, for the y-axis, trying to see now if I can get this. There we go. Now notice here, for the y-axis, as x approaches positive infinity, as we trace the graph along the right-hand side, as we go towards positive infinity, this line here, our function, gets closer and closer to 3, but never crosses 3. Because what happens after 3 here is we have a jump in our function along the y-axis. And here we have that jump. And if we go to negative infinity, we see the same thing. As we go to negative infinity, our function, our line, gets closer and closer to 3 here along the x-axis, but never crosses it. Okay, so there we have our asymptotes, the breaks in this function at x equals 2 along the x-axis, and then at x equals 3 here along the y-axis. All right, I'll do a rough sketch of that here as well. Okay, so based on the pattern that we found for this function of f of x, there we go. Okay, let me draw these two lines again. Doesn't look straight to me. All right, so here we had a vertical asymptote at x equals 2. Let me use a line paper. That's what I should have done in the first place. Okay, let me erase these two lines and draw them again. All right, so let's do the real quick rough sketch of our graph here. All right, so here we have vertical asymptote at x equals 2. I'm going to go by zeros and ones here. So 0, 1, 2, 1, 2. So here we have our vertical asymptote at x equals 2. Let's say our VA at x equals 2. And then here we have a horizontal asymptote. I'll do a different color for that one. At y equals 3. So we have our horizontal asymptote at y equals 3. Okay. And then between these two asymptotes, that's where we find this break in our function. All right, so here we have the first part of our function. And then here we have the second part of our function. All right. I didn't really like that one. So this is, all right. Dang it. I can draw this right now. All right. So here we have the first part, and then here we have the second break in that function. All right. So these two asymptotes splits our functions into these two parts. Okay. All right. So here we have this horizontal asymptote y equals 3 for this function of 3x plus 6 1 x minus 2. And the vertical asymptote which you found earlier at x equals 2. Okay. Let's do 2 more examples here. Let's do another example of finding the horizontal asymptotes from the second example that we worked on, which was this quadratic over this other quadratic. All right. So now for this next example, let's find the horizontal asymptote of our function of x, of f of x, which we defined as x squared plus x minus 6 over x squared plus 4x plus 3. Okay. So again, to find the horizontal asymptote, it will be equivalent to find the limit as x goes to infinity. You don't have to find both sides, as x goes to infinity is good enough, of this rational function of x squared plus x minus 6 over x squared plus 4x plus 3. Okay, now again, we're finding the horizontal asymptote. There is no need to simplify. All right, do not simplify your rational function. Leave it as it is when finding the horizontal asymptotes. What we want to do here is we want to divide each term by the highest degree power of x in the denominator, which in this case will be x squared. So everything on top and everything on bottom will be divided by x squared. All right, so this will be equivalent now to find the limit as x goes to infinity of x squared divided by x squared plus x divided by x squared minus 6 over x squared all over here. Also in the bottom, x squared over x squared plus 4x over x squared plus 3 over x squared. All right. And now apply the rules of limits here, as we did with the last example. Oh, actually, before we do that, simplify what we can. So x squared over x squared, that just becomes 1. So let's find the limit as this goes to infinity. So again, these two, x squared divided by x squared, that's going to cancel out even if it's with just 1. Oops, a different color. Plus x over x squared leaves us with 1 over x minus 6 over x squared. Again, we just canceled here. X over x squared cancels out. 1x on top cancels with 1x on the bottom here in the second term. And in the bottom, pretty similar. X squared cancels out. And then for the second term, we have 4x over x squared. That x on top cancels out with 1 factor of x on the bottom. And then 3x over x squared just remains the same. So on top, we're going to have 1 plus 4 over x minus 6 over x squared. Now we want to find the limit of each term as x goes to infinity. All right. So again, limit of a constant is just that constant. So it's just going to remain 1. And once again, limit of a constant over a changing variable, that's going to become 0. So 1 plus 0 minus 0, again, 6 over x squared, constant over a changing variable. As it goes to infinity, this will become closer and closer to 0 over limit of constant. Once again, limit of 1 is just 1 plus 0 minus 0, leaving us with just 1 over 1, which is the same thing as just 1, meaning this rational function has a horizontal asymptote. Has a horizontal asymptote at x equals, not x, y. Y equals 1. Y equal